All right, we want to welcome everyone. I'll make one more request that if you are sitting next to an open seat, scoot over toward the middle so that lecturers can have a place to sit. My name is Tim Swindle. I'm the director of the Lunar Planetary Lab. I'd like to welcome you here today. Okay, I'll do this. How many of you were here for one or both of the first two talks? Many of them. So, thank you.
You already know it all.
Yeah, you'll get another perspective. If you were here for earlier talks, you know that I was doing this whole spiel about things going on related to Moonfest and that sort of thing. It's going to be a shorter spiel this time because many of the things that were going on today have already happened. Of course, this is the 50th anniversary of the Apollo 11 landing. I think actually the spacecraft, the Eagle has landed, was about the anniversary, I think was 15 minutes ago, something like that. So anyway, so July is officially Moon Month in Tucson by proclamation of the mayor. We have put together something we call Moonfest. We have events around campus and around town. As I say, many of them around campus are finishing for today, but Planetary, Science Center, next door, they have family-oriented events and they have their planetarium shows. They don't end today, but the Apollo 11 oriented one called Cratering does end at the end of the month. Special collections at the U of A library. Today is the grand opening of their moon exhibit, and I think they may be closed by the time we finish with this lecture. Closed for the day, but they will be open. They'll be in December, so you can take a look over there. They have all sorts of things. They have things like rare books, so they have original editions of things by Galileo and Copernicus. They have a bunch of memorabilia from Whitaker, whose papers they have, the late Whitaker, who worked at LPL for a long time. Although my favorite piece of Whitaker memorabilia, which is an autograph, a book autographed by the Apollo 12 astronauts, thanking him for finding a landing site for them. They don't have that on display over there because it's on display out here. We have a number of other things on display, lunar rocks, that sort of thing. Special collections also, my favorite thing in special collections is, did you talk about the rectified lunar atlas?
Not yet.
Okay. You're going to talk about it? Or no? Okay, so when Bill talks about the rectified lunar atlas, the globe that he used is on public display. I think this might be the first time it's ever been on public display. That's worth seeing. There's also an event this evening at Desert Museum where one of our graduate students, Lance Stotterman, will be speaking at 8 p.m. about upcoming lunar science. Now, I hadn't mentioned this earlier, but we are also supporting an event in Phoenix this evening, which is why I'm going to leave right after I introduce Bill, so I'm not that I don't want to hear it. But there are all sorts of other Moonfest events, talks, exhibits, that sort of thing, and you can find them all at moonfest.arizona.edu, and I encourage you to take a look there. This is the last of our 3 talks today. The speaker is Bill Hartmann, who was a graduate student here before here was here. So Bill was one of the original Lunar Planetary Lab graduate students, and I think he's going to be talking about how they ended up this building. But he also, after getting his PhD here, was one of the founders of Planetary Science Institute, which is still going strong in Tucson, in which he is now his title, I believe, is Senior Scientist Emeritus. Want to rub it in, right?
What it means is just I'm not bringing in any money anymore.
Yeah. And among other things, Bill is one of the people responsible for the current leading theory, current as in for the last, I don't know, 30, 40 years, leading theory for the origin of the moon. And he'll be talking a little bit about his perspective on how lunar science kind of got started here. So, thank you.
Here in Tucson in 1960, and this was Stewart Observatory across the street, which is, if you're standing there now, there's a big 5-story building. This building wasn't there yet. the Kitt Peak building across the street had just been built. My comment about, we had this working a minute ago, is the issue.
Technology.
Oh, okay, I see what's going on. Yeah, there's an arrow in the backward direction, no arrow in the forward. So we had snowfall, real snow, and we also, you could drive your car into that nice little parking lot and park for free. It's halcyon days of the past. So 57, it was the first Sputnik, I think everybody knows, and there was a huge reaction on the part of Congress and educators in the United States to get more science going on. So it was a great time to be starting a science career. Kuiper had just come from Chicago, where he had started, well, he was a well-known astronomer there at University of Chicago, and had started several lunar atlases and got a very nice deal to come out here, partly because NASA and I guess maybe NSF, National Science Foundation, had started a program to advance sort of the grade B plus American universities into grade A research institutions. And the University of Arizona was one of those. So there were a large amount of grant money, and Kuiper was able to start a whole new program, and this new building, this building that we're in, was part of the result of that. So April of '61, an exciting time. Yuri Gagarin went around the world for the first time, first human being around the world. As a result, the next month, President Kennedy gave the famous talk about putting a man on the moon. Least important thing at that time was in June, I arrived. And that whole period then was very active in terms of just beginning planetary science. I mean, there was a joke among astronomers that nobody liked the moon because when it was out there, it lit up the sky and you couldn't see all the faint galaxies and stars that the astronomers were interested in. And Kuiper was one of the very few people who was at all interested in the planets as a topic for research, which is why I came here. Now, there's people who think we were just dorky graduate students. This is my buddy Dale Cruikshank. Anybody heard his name? He was another student of Kuiper's, kind of my best buddy. And I just wanted to show that we were really on the cutting edge of the hippie revolution. I don't know why everybody's laughing. I'm lurking there behind Gerard Kuiper, who is looking at one of the first photographs of the far side of the moon, which again was Russian. So he had set up as a second atlas in the series this globe, which is what Kim was just talking about. Now, Kuiper had collected the best photographs of the moon from around the world, from a lot of leading observatories. And these were usually glass plates, and the image of the moon would be about that big, but very high resolution. And so he put into practice an idea that had been floating around, but really nobody had worked with this idea before, to take those photographs and project them onto a globe. Now, why do you do that? You've got to remember the moon keeps one side toward the Earth. So if you're the Earth and I'm the moon, you only get to see this side. And in particular, I'm going to talk about the situation where, suppose this is the only thing you see of me, but there's some kind of funny formation over here, right? But you'd be hard put to make a drawing of what that would look like if you could actually come around and see it from this direction, because you're only getting to see it this way. So in year, it's kind of a hard thing to make out what it is. And that's what happened here. I had, let me say, I had been an amateur astronomer. I knew my way around the moon and did a lot of observing the moon with an 8-inch telescope that I had built. So Dale had also built a 12-inch telescope. And our whole group, those first few years, were had kind of come out of that amateur astronomy atmosphere. And I had also been reading a lot of the lunar science that was going on. So I was kind of prepared that one day when I walked in, let's see, sorry. One day I walked in and I was looking kind of over here at this edge. And of course, the backside of the moon, we didn't even need to build a full globe. This was a hemisphere, actually. But there would have been stuff back there that we'd never see. But I looked over at this spot like about there. And, oh, sorry, I got out of order, didn't I? Okay, so let me back up a second. One of the first things that was done with that globe was that people were concerned about the reality, I'm having trouble getting to this, the reality of this first photograph that the Russians had reported from the backside of the moon. And there were even newspaper articles pointing out, you know, there's really not much there, and this thing is probably fake, which it wasn't. But Whitaker was a very clever guy from England, hired by Kuiper, and he used the globe about the time that I got there, and projected our pictures of the moon at that lighting. So this is the Russian photograph. This was what showed up on the globe. All of this part is on the far side of the moon. Ewan walked around to the back of the globe and photographed from the same direction as the Russian lander, or the Russian spacecraft that orbited the moon. But you can see the same features. You can see, you know, quite a bit of detail and matches up. But we know now that the Russian scientists really were perfectly truthful about what they were doing there. And I might say that before I go on to talk about things that I did, I mean, there just wasn't much going on in planetary science. And I look back now and really realize that there were a lot of kind of clear things that you could do if you were really interested in the subject. So I'm going to talk about three things that I did in particular in those first few decades. So there's discovering this big impact basin. There's using the craters as a way to get information about the age of surfaces. And then this is the ideas that we came up with for the origin of the moon. So there's the globe. And there I am looking at it. And here is kind of what I saw when I walked in on the edge of the globe. This would have been the backside of the moon. This was a photograph with the lighting from the sun would be from over in this direction. And so you really see nice shadows and relief here. And look, there's this big arc here, and there's another arc there, and there's part of something there. And nobody had ever drawn or mapped either here or even in the other basins, the idea of kind of a bullseye-shaped concentric structure. But this had, you know, a look of an impact feature. You can see some kinds of radial structures going out there as well as the concentric structures. And so I took more photographs. I think this may have been the actual one that was on the globe when I first saw what was going on here, and took them over to Kuiper, and he immediately agreed with me that this was an important discovery, and he was gracious enough to let me be the first author. So here I am, a first-year graduate student, you know, writing a paper with the great man, so to speak. 1961-62 is when that is. 67, there was the Orbiter 4 that went around the moon and took some photographs from around on the other side. So this is a kind of a nice matchup. This crater is that crater. This crater is that crater. You know, we're seeing that peak there is probably just part of some of this material, I guess, in that ring. This was important because there were still arguments going on as late as 60, 61 as to whether these craters on the moon were volcanic or impact features. And this helped solidify the idea that they really were impact features, because you've never seen a volcanic complex or structure of that size. I mean, this is something like 400 miles across, 600 miles in that ballpark. This is the kind of thing we have today. And the last speaker was talking about some of the gravity and probably the altimetry work. There's laser altimeters. You're flying over. I mean, here you come. It takes this long for the signal to come back. This long for the signal to come back. Whoops, the signal came back just in a half second. And so you get topography from just bouncing little laser beams off the moon. What this box is about is pretty much what we originally saw. That's the only part of it we could see. There you can see the radial structure a lot better than down here. So you can really believe that something came in and hit that. The other thing that was going on at that time was a guy named Gene Shoemaker. Has anybody heard that? Geologist, Flagstaff. And he was at the same time starting the U.S. Geological Survey astrogeology office. And so they were very keen, they were very interested. I remember Jack McCauley, one of their guys, came down and was amazed at kind of what we were seeing here. So that the Kuiper's atlases, which were photographic, and particularly the rectified atlas looking straight down, were good base materials for their maps. And they were making classic geologic maps with stratigraphy, this feature is on top of that feature, and so on. Here's a photograph of a young woman, a planetary scientist. This is the Orientale Basin up there. I just put it at the top. There's kind of a zone around there that you don't see much. And then she was mapping kind of smooth materials in valleys. And you kind of get some sense of maybe radial structure there, but also, and this is important in modern lunar science, what's going on today, look at the area of the moon that's somehow affected by this impact structure. So these big impacts are having some effects, whether that's all just ejecta, or is that fractures that opened up, or even flying, low angle flying debris coming and sort of gouging their way through mountains. Nobody seems to be very sure, I would say, on what that is. But years later, it made me realize something that I think was true in my own career subconsciously. But the fact that in the 60s, when we found that thing, everybody else was trying to see the tiniest details that you could see on the moon. And that's like half a mile. I mean, that was the best you could do with telescopes from the Earth. But everybody was concentrating on getting the fine detail. And the fact that we could back away from the moon and discover some enormous thing that nobody else had ever noticed, made me have, I think maybe it affected the way I do science, because it's kind of like, even today, a lot of young scientists, graduate students are taught to make numerical models of something, and they get very detailed, and they kind of live within the space of that model. And what you often need to do is back away and see everything else that's going on, what's coming in from other kinds of observations. So, so this is an ad for students to think in big terms and not just details. So the next item is, what can we do with all these lunar impact craters? That's one of my paintings, by the way, of one of these big basins forming on the moon. Backside of the moon, what we can see today, you don't have too many of these dark patches. In fact, these are actually on the front. You can see these from the front. This is the front side over there. But just incredibly densely cratered. But then you go and look at these lava plains, the dark features on the moon, and they don't have many craters. And what is that telling us? You've got heavily cratered areas, lightly cratered areas. So what I started doing in the mid-60s, still a graduate student, was to make a diagram. And sorry, these numbers are kind of small from the back, but this side is the number of craters per square kilometer, or or number per square mile. So how many craters you see in a given area. This is the size of the crater. And up this end is 256 kilometers, so 100 miles, something, 250 miles. One kilometer here, and it goes all the way down to 16 meters. So now the quiz question is, what is the curve going to look like? I mean, if they're all the same size, I mean, if there's this equal number in each size band, then it's going to be flat. If there's more big ones than small ones, it's going to go like that. If there's more small ones and not very many big ones, it's going to go like that. So anybody have any choices on that? Yeah, it's what I like to say is, you know, if you break your grandmother's vase, you know, there's one or two big fragments and lots of little fragments. And these things that are making the craters, let's back off and think of the big picture. These are fragments of asteroids coming in from space. The asteroids are hitting each other and breaking each other up. So that size distribution for the meteorites is the same kind of slope that we see here, that we see here, going that way. And this was the curve for the heavily cratered regions, and this is the curve for the lava plains. And there was a factor of about 30 more craters per unit area in the crowded areas. And that tells you something about age, ultimately. Because if you're accumulating craters by impacts, then the more impacts you have, the older the age. And so all we had to do is then calibrate that. And from the first kind of calibration was in the summer of '64, before Apollo got to the moon, we sent these rangers, and Kuiper was a major scientist in that. They were spacecraft with cameras, kind of TV-like cameras, that took pictures all the way in and crashed on the moon. And that was the first time we got down to very small crater sizes. This is 2.8 kilometers wide, so maybe a mile and a half wide. And you could get down to 10 meter size objects. So that's, like I said, everybody was trying to concentrate on how can we see the smallest details. But that allowed me to, I remember having a kind of a eureka moment. Kuiper had sent me to Hawaii, of all things, as a graduate student in '64 to live on Mauna Kea at 9,000 feet and drive up every night for 14,000 feet on this lonely dirt road to make observations of how good was the top of Mauna Kea for observing. Because another thing that Kuiper liked to do was create observatories, and particularly get above the water vapor so you could use infrared detectors. So Kuiper had sent me down there, and I was driving down the mountain one day when just after Ranger 7 crashed, and I realized, wait a minute, I'm going to be able to take those curves, those crater curves, and extend them all the way down to 10 meters or so. So I did a lot of that. The bottom line is that this is a kind of a template. Again, number of craters per square kilometer, the diameter, 1 kilometer here, 1 meter down here, that's just a yard. 250 kilometers at the big end. This line is interesting. I'm sorry, my thumb is overlapping. Sorry. This line is very interesting because I found within a few years, as we started sending probes to other planets, that on the other planets and other moons and even asteroids, you just never see very often any crater densities above that line. So what's that telling you? That's a saturation where you're forming new craters, but there's so many craters already there that as you form new ones, you're erasing old ones, and so it sort of stabilizes around that line. And we have, by using the Apollo data, which dated the 6 surfaces where they landed, I could then calibrate all of this and say, okay, for a 1 billion year old surface, it's going to be this curve, and for 4 billion years old, it's going to be this curve. So that's what's going on here. And this is like a 1 million year curve right there. Sorry, those numbers are so small. This is 1 billion years right there. This is 4 billion years, and then you're pretty much hitting saturation about that time. So the craters had a purpose or function that way, but at the same time, in the early 60s, they were just walking in on the Earth to the fact that that big impact craters occur on the Earth. In fact, that was one of the problems. Was the moon is full of impact craters. Why don't we see them on the Earth? And the basic answer is that plate tectonics and geology is so active on the Earth that surfaces are crashing into each other. We have erosion, we have water, rainfall, all of that. So you just don't have surfaces on the Earth very often that are older than a few 100 million years. But central Canada is one of the oldest surfaces, a kind of stable core of North America. And the Canadians were discovering circular lakes with their aerial photography. They were doing aerial mapping of Canada. And a lot of these circular lakes, they would send crews out. Sure enough, there were meteorites and shocked rocks and so forth. So we had, even before Apollo, we had a surface up there in Canada that was a few 100 million years old, and I could count the number of craters on that surface and then use that and say, well, the moon is being hit by about the same number of things that are hitting the Earth, so I can use that to estimate the ages on the moon. And I came up with a paper that talked about those lunar lava plains, which are called maria. Maybe some of you know, that was the Greek word for sea, mare. And so the people like in Galileo's generation thought those dark patches might be seas, and so they got this name Maria. I call them lava plains just to be more plain. So that age was what I put in my paper, and then when Apollo got there, the samples from the lava plains were in that ballpark. So I like to say that this system of using craters to get ages has had some success, and I kind of emphasize that not just to be self-serving, but there's been a certain amount of controversy and criticism about can you really use these craters to do this, and naturally there's all sorts of problems. But I think, again, if we kind of back off and look at the big picture and not try to quote 4 significant figures and just say, you know, that we're talking 2 billion years, not 4 billion years, or vice versa. Those kinds of accuracies are actually very useful for planetary science. Now, another thing that's tied into all of that, and the last speaker was just ending on talking about this when I came in, there is this, what we would call soil, and as some of you probably heard his discussion about that, that's not quite the right term, because soil, the word on Earth means organic material breakdown of rocks and so forth, and there isn't that organic material. But this is a finely pulverized material. You can see the tracks of the rover going around here and footprints, tracks out there. Why is that stuff all ground up? Well, it's because of the meteorite impact rate. And so this idea that there was no erosion on the moon is actually not quite right. And that plays a real role in lunar science, because what I've just been doing in the last few years is kind of going back and looking at the history of some of these ideas. And it's pretty clear that before Apollo, the scientists who were brought in to plan those missions thought that let's say this is the history of the solar system. Here's today, and when were the planets formed? That was 4.5 billion years ago. So there's no erosion on the moon, right? So the moon is going to have all these rocks that are just lying around from 4.5 billion years ago all the way through. If you just collect a bunch of rocks, you're going to get the entire history of the solar system. So one of the puzzles was when they bring back the samples, and they've been looking at them for the last 40 or 50 years, it's very hard to find samples, particularly impact-related samples, older than about 4.0. So you don't have any impact melts. In fact, there are a few scattered ones, but not much in that zone. And so the initial conclusion, and this is a paradigm that has been going on for 45 years now, was that there were almost no impacts until about 4 billion years ago. And then a lot of the big lunar features formed at 4 billion years ago. And that's been the going theory. And you'll still read about that. I'm just reading some of the popular science magazines that came out like this week. And because they're all talking about what have we learned from Apollo. And they all keep quoting this terminal cataclysm of 3.9, that's one of the big things we learned. And I think that's turning out not to be true, that it's partly built into what they expected to find before Apollo, that they thought they would find these rocks back here. They didn't find them, so the answer must be that there were no impacts. And the direction I think we're going is that those big impact structures affect a lot of the surface of the moon, like that one picture that I showed you. So if you look at the lunar landing sites, and they're all not terribly far from one of the biggest basins on the front side called the Imbrium Basin. And it's looking like most of those landing sites have Imbrium debris thrown on top of the landing sites. And the Imbrium Basin is clearly dated at 3.9. So it looks like we're kind of corrupted by the 3.9 material. And one of the interesting things is Tim Swindle, who was just here, he and his graduate student, Barbara Cohen. So we had, Cohen was the lead author, Cohen and Swindle and another guy named Kring. They had this bright idea of using the new techniques on the old Apollo samples that could date very fine material, little tiny bits of impact melt in some lunar meteorites. So now we're not limited to the samples from the Apollo sites. Rocks are being blown off the moon all the time by impacts. Some of those rocks manage to fall on the Earth. So we actually have identifiable pieces of the moon now on the Earth that we can get even without going to the moon. The only problem is we don't know where they came from on the moon. But actually they did some chemical analysis and tried to pick samples that were not like the Apollo samples, which should mean they were getting other parts of the moon, the backside. And their data don't show any spike at 3.9. So it looks like what's really going on is that there wasn't a big spike at 3.9. And now this is partly me speaking, other people would take issue with this, but I think what's likely is that there was very high impact rate, a lot of debris left over from when the planets formed. Debris is gradually getting used up. It's either aggregating into asteroids or the asteroids are hitting the planets and the debris there's less and less debris. And 3.9 is the age when these rocks begin to survive. That there were lots of them being created back here, but the ones that we created here get pulverized by the impacts in this period, and the ones that are created there get pulverized by these impacts, and then finally you get to a point where the impact rate is low enough that you don't destroy them. So that's a controversy that's going on right now these days. But certainly the cratering has a role in creating that regolith. Regolith is being lithic for soil, for rocks, for stones, and regolith meaning region. So it's the rocky soil material that's all over the moon. And I mentioned saturation. So you can do all kinds of interesting things with this diagram. I'll just talk about one more thing. This is an early set of data that I made counting craters in different parts of these lava plains. And you can see that there's a steep part as you get down to a few kilometers and a few hundred meters sizes. And then it hits the saturation curve. And if you add up all the area covered by these craters and these craters and these craters and these craters, all the way down to about here, that's when you hit 100%. on average, 100% of the surface has been hit by stuff bigger than that. And that size is something like 40, 60, 80 meters. And if you think of the depth of a crater is about a third of the diameter, so a 60-meter crater, 20 meters deep. So everything's been excavated at like 20 meters. That's basically the depth at which they measured. The Apollo astronauts measured the depth of the regolith. So that all kind of fits together. So that's just kind of one example of how you can use these curves to think about what's been going on. And then finally, the origin of the moon. Going into Apollo, there were three ideas about the origin of the moon. There was a major issue that we knew the size of the moon and we knew the mass of the moon from some things about orbital motions around the Earth. So you know the mass and you know the volume, then you know the density. Well, the density of the moon is something like 3.3 grams per cubic centimeter, and that's about the density of rock. You know, ice and water is 1, iron is 8. The Earth is 5.5. So they knew that the moon does not have a big iron core like the Earth. Where is all that iron? Why didn't the moon get the same composition as the Earth? And there were different answers before Apollo. One of them was that, trying not to get them mixed up. Well, the basic, I'd say the most popular idea was that the Earth and the moon had formed together at the same time. But that had a terrible problem, because why would the iron all end up in the Earth and not in the moon? And people tried to make kind of complicated dynamical models of that, and nobody was very happy with that idea. Another idea was somehow the Earth was spinning very fast at the beginning and it spun off some material. But that didn't really, the physics of that never really worked out, because there isn't that much angular momentum in the system today, and so that didn't seem to be satisfactory. And the other idea is, oh, well, the moon must have been formed in a very distant region where there wasn't so much iron, and then it was moving through the solar system and it got captured into orbit around the Earth. And the problem with that is it's very difficult to capture something like that, because you got to slow it down to keep it in orbit. Otherwise, it comes in, goes by the Earth, and it's deflected by the Earth, and it goes off in another direction, but it doesn't get captured. So that's what we were stuck with. And so a few years after the samples came back, one of my buddies at the Planetary Science Institute, which we had started by that time, and I'm actually now talking about 71, 72, 73, I got an idea that maybe there could have been an impact which would have blown rocky material off the surface of the Earth, and that's what the moon would be made out of. And my buddy Don Davis is an interesting guy. He's still in our group. He's gotten older, I don't, of course, I have. And he had done a lot of orbital work. He took physics here at U of A, another alumni, did a lot of studying of orbits and how things move. And his big claim to fame, really interesting, is that he was on the Apollo 13 team and gets, as I remember his story, he gets a call one night, we've got this terrible problem, and they all come into work in the middle of the night, and I think it was the middle of the night, and they have to figure out how to get the Apollo capsule around the moon and back on heading to the Earth in the right path to land. And so they did that and managed to bring it back. So he was very experienced in that kind of thing. And he did a whole set of calculations, which I have here someplace. Let's see. Well, he did some calculations and got that what we were trying, let me back up a second. what we were trying to do was figure out if the Earth is forming, and the Earth and the other planets are forming from asteroidal-like debris. In other words, let's go back to when the sun formed. At the beginning, there's this nebula around the sun that's got dust particles that are condensing out of the hot gas. And a lot of dust particles, they're all moving around in circular orbits. Neighboring particles can stick together when they hit. The more particles you have, the easier it is to capture more particles. So there's a growth. There tends to be an accumulation, or they call it accretion in planetary science. The asteroids were accreting. They were getting up to 1 mile across, 10 miles across. Eventually, you had the largest one in each zone from the sun, going outward from the sun. In each zone, there was one largest one, which became the planet. So our idea was, couldn't there be a second largest one and a third largest one? And it had to be that. So what were they like? How big did they get? And he did some calculations, and we concluded there could be second largest objects up to the size of Mars, which is about the size that you need to do this. So the idea was you hit the moon, you hit the Earth with one of those objects. Now, it solves the problem, because if all the iron went to the center of the Earth as fast as the Earth was forming, then the outer part of the Earth is just rocky the way it is today. And you blow off this outer part of the Earth, and a little bit of it goes into orbit, and so the moon is made out of that crustal and upper mantle rocks. Then there was another interesting thing that came up at about that same time. We gave that paper in a 1974 meeting, and then we published it in 75. So that's when that theory got started. Right about that time, there was the discovery that from the lunar samples, that the isotope chemistry, and what does that mean? That means, like, you're looking at a rock and it's got oxides in it. The oxygen has oxygen 16, oxygen 18. Those two isotopes have a certain ratio. Those ratios are wildly different in other parts of the solar system. And the further away you go, the asteroids from those regions have more and more different isotopes than the Earth does. So that seemed to be, we were saying, hey, this fits our theory, because we want a local object. That's what we were talking about in the first place, and the local objects would have had the same chemistry as the Earth. In the distant asteroids that we get meteorites from, they don't have that chemistry. So hey, this looks pretty good. But what happened, kind of the history, I mean, this is just sort of fun science history. This is just a visualization of the outer part of the Earth getting knocked off. And that's actually based on computer models that people are doing of this kind of event. One of the results is that of these models is that the moon gets a little more of the impactor than the Earth does. So the moon has a higher proportion of that impactor than the Earth does. Okay? Now, this is the actual calculation that Don made in our first paper. It's a little hard to follow this, but this is the size of the growing objects, and you're starting at time 0 here. 10 million years, 20 million years, 30 million years. Here's a whole bunch of objects. These guys are all growing slower, and these are getting pretty big faster. Here's the biggest one, which the bigger it gets, the more it pulls in other objects because it has more gravity, so it grows very fast and becomes the Earth. And so there's the size of the Earth up there. And then this one is the second largest one, and it ends up hitting the Earth and doing the job for us. What happened, just to give you kind of a little flavor of controversy in science, if you're going to go to a big scientific meeting, it's good to get the Royal Society in England to sponsor the meeting, because they bought up some of these big old grand houses like Downton Abbey, and they put us on our bus. We had an initial meeting in downtown London. It was public, and then we all got on this bus and drove out to Chicheley Hall, and we all got to stay there, and that was a very nice place to have a meeting. I recommend it. And that meeting was about an isotope crisis, which much to my dismay was declared about 2010. That the idea was that it would be unlikely to hit the Earth with something that was exactly the same composition as the Earth. And if it's got moderate difference in composition, like I said a minute ago, the Moon ends up with a little bit more of the impactor and the Earth a little bit less. So there still could be detectable differences between the Earth and the Moon. Why don't we see these? And so therefore, the argument was that the whole giant impact theory is now in trouble. So that's why I wasn't happy with that. But you know, I keep telling people I don't want to be the old guy who's defending his old theory, you know, it's wrong. So this meeting was quite interesting because there was a lot of discussion of this. And you know, what I began to think is, wait a minute, these guys that were talking about this isotope crisis were basing it on this model, which is a bunch of assumptions. And the actual observation is that the Moon is rather like the Earth and very slightly different. So we should start with that. So the first conclusion, it was not hit by a very distant object. And most of this meeting was devoted to people who were saying, well, the models tell us that it was hit by a distant object. So it was not hit by a distant object, and is that plausible? And what I came away with, or what I tried to emphasize in my talk at the meeting, is there is a type of meteorite that has almost exactly the same isotope composition as the Earth. And it's you can't make the entire Earth out of that type of meteorite, but if it was the kind of object that was growing nearby the Earth someplace at the beginning, it would have a high chance of hitting the Earth. So I'm thinking that that's probably what actually happened. And the cool thing was that this, as I said, this was sponsored by the Royal Society. Now, the Royal Society in England put out the world's oldest scientific journal. So it was really great to have a paper in this journal. It was started by Isaac Newton and his buddies, you know. And on top of which I got to have my painting there on the cover, so that was fun. There it is. And I think that's the end of the talk. Thank you very much. I have royal permission from Tim Swindle to do questions and answers. So do some of that.
Hey Bill, the previous speaker talked about the Moon being lopsided. You were talking about giant impact craters. There's something big under South Pole Aitken Basin. They're finding a big mass under there that seems unusual. What's up with that?
There may be, in general, we think that.
Repeat the question.
Repeat that. So, as this last speaker mentioned, the gravity shows some evidence of massive objects at depth in certain parts of the Moon. And the question, I guess, would be whether are these remnants of impact materials? You know, normally the thing you say is that the impactor gets completely destroyed in these high velocity collisions. On the other hand, if these were early collisions and things were not coming in at such a high speed, they were neighboring objects, they would actually fall into the Moon at a little bit lower velocity, so maybe some of that material survives at depth. But I don't think we actually know the answer to what they're seeing. Another aspect is that it's been known for quite a while that the big impact basins all have what was called mass concentrations under them. But that is more about you create this big hole, and then the hole starts to fill in. Partly the walls are slumping, but there's material coming up from below, particularly if there's molten material down there, it will all be coming up and filling it. So the massive stuff from the dense material from the mantle moves up under these big impacts, and that may be the other solution. Yes. Yeah.
The whole idea little closer. The whole idea of the big impact. I've always wondered what kind of relative speed did it happen? The second largest Earth-like body coming in, did it?
Well, if you just park an object above the Earth and let it fall into the Earth, it hits its what's called escape velocity, which is also the velocity that the Apollo astronauts need to get, well, not the Apollo astronauts, but astronauts who are trying to leave the Earth have to get to escape velocity to get away from the Earth's gravity. So those two, one is just the backwards motion of the other, but if you start from 0 speed out here and just fall into the Earth, that's 11 kilometers a second, I think, something like that, 11 or 12. However, most of the meteorites that hit the Earth today are coming from the asteroid belt, so they're moving around the sun already relative to the Earth. So they don't start from a 0 position, they're already moving, and they tend to hit anywhere from 11 to 30 kilometers a second. So the earlier, if you're hit by a local object, that's relatively slow compared to what we're being hit by today. And it would be some kind of velocity like 11 or 12 or 13, 15 kilometers a second, something like that.
So they just kind of fell into each other.
Yeah, because think of, I always like to give a racetrack analogy. The sun is in the middle of the racetrack. The cars are all driving around like this. They have to drive parallel to each other, more or less, to avoid hitting each other. And if one car gets disturbed for some reason and starts cutting across all these lanes, you're going to have very high-speed collisions. And so the normal situation in this nebula of moving objects is that things are moving together fairly closely in parallel tracks. So they, in fact, fall into each other at low speed. It's like two cars racing and they touch each other. And so they get at low speed. But, if somebody's driving diagonally across trying to, start at the center and drive out, they're going to be hit by a high velocity car. There's the reason that things start to depart from the perfect racetrack is that once the planets grow, so once the Earth gets as big as it is, then a neighboring race car, a neighboring asteroid comes by and gets disturbed off at an angle. So you in fact have the solar system with a certain number of things that are going in elliptical orbits in all kinds of orientations and hitting each other at very high speeds. And that's in fact why the asteroids start breaking each other up, because once they get big enough, they can disturb each other in their motions, and then they hit at high speed and break each other up. So most of our meteorites are fragments of the asteroids that are broken up. So there's a whole kind of story there to answer your question.
Thank you.
Yeah. Yes, sir.
When like you guys like at the conferences and stuff, when you disagree, you kind of feel this thing, and you. But I mean, scientists, they're not married to their theories. So when you guys disagree, is it just because you've done more work on that specific thing and you know more about it, and then therefore you believe in it more? Like, I guess time will give the answer to everything, but why can't one say?
So it's a question about scientific disagreement, and first of all, why does it arise, and how is it sort of handled? What does it feel like when you're at the meetings? Planetary science in general, I think, is really good. We really have a sense of we're all in it together, and so the arguments are not. They don't get personal, I would say. And I actually credit Carl Sagan with some of that, because the big planetary division of the American Astronomical Society, we call it DPS, a Division of Planetary Science, they hold an annual meeting. Carl was one of the founders of that. And I can remember him at some of the early meetings when an argument would get started between two people. And that happens. I mean, here I'm the speaker and there's somebody over there and he just doesn't buy what I'm saying. And he gets up and that can devolve into a real argument, you know, well, I'm not stupid, I know about that. And it gets to that point, and usually the moderator is supposed to keep things under control and say, well, you know, I guess you guys should discuss this out in the hall. It's time for our next speaker. The way you get through that. But I remember Carl in a couple of instances like that where kind of an argument started, and he would, you know, you put your hand up in the audience to ask a question. So in the guise of asking a question, he'd stand up and kind of give this marvelous little speech about how we're all in this together. We're the first generation to see any of these things with our different spacecraft, and, you know, get everybody feeling good about being there again. So I think we kind of started off in that way. The biggest arguments I've ever seen are between biologists, for whatever reason. Generally, I think it's a good field in that regard. Also, I might just say that it's a very good field for women scientists, and I think you know, Carl had some influence in that. In our institute, we actually have, we have about 100 scientists, and 45% are women scientists. One reason is we can go out. We're not like a faculty, like Tim's job as head of the department. He can't just hire 10 new people. He has to have that in a budget. Ours is all soft money. You have to write proposals and get funded. And if you can stay funded at full time, that's great. And some years most of your proposals are turned down, and that person might go to half-time work or work on somebody else's project. But you know, so our institute is a little bit dicey because it's nonprofit and you have to be funded. But we are able to hire multiple people, and they can be either gender. But yeah, basically a good field, and there are arguments. And the reason that they can come up is that, you know, here I'm person A, and I've been reading these papers in this journal, and here's person B, and he's reading, you know, I'm reading about petrology of the rocks, and this other person is reading about the orbital theories, and well, the orbital theory says this, and that doesn't fit with what you're saying about the petrology, and then, you know, neither one quite knows enough about the other guy's field, so you have these kind of different perceptions of what's going on. And maybe another question. Yeah.
So you talked a lot about using the craters as an indicator of time period, but is there a whole debate about the origin of the collisions altogether? Like, where is all of this coming from? What's the theory of why some periods are delivering it?
So yeah, the question is that when you're using the craters to interpret the history, are there problems with different ideas about where the objects are coming from and so on? One immediate answer is that there has been a controversy for a long time that what you would like to be counting, if you could do it, is just each primary impact, meaning from a meteorite in space. A problem is that a big impact throws out lots of rocks, and those land over here and over here and over here, and those make what are called secondary craters. So once you get down to small sizes, you're dealing with a lot of secondary craters, and those don't necessarily happen randomly because, you know, one object can throw out 1,000 secondary craters. So there's been arguments about how to handle that, and but you mentioned the idea of things coming from other places, and that's really part of, I think, a core argument about the origin of the moon. Because if you buy into the way they did in 2010, there had been all these models, computer models being made explicitly made to try to explain why you didn't get impacts in this early period, which I think you were getting, but you just can't see them. But if you didn't get any, then you've got to come up with some model of the solar system for why are the asteroid pieces hitting today, but they're not hitting back then. And there were papers like that. And so you had a whole group, sort of the dominant group, like at that meeting, coming from that part of science. And so they were, as I said, assuming at the beginning that the objects hitting the Earth were coming from a distance. Because the solution to this problem was the reason we weren't getting things from hitting the Earth at that time was that the outer solar system hadn't finished forming, is basically kind of what it's about. And that finally the giant planets got big enough and they were moving around, which seems to be a pretty solid result that they may have drifted around before they got in their present orbits. But so if that drifting started at 4.0, then you'd have the inner solar system hit by a whole swarm of things from the outer solar system. And that's where they were getting their impact from. But as they themselves said, I mean, the moon wasn't made out of stuff like that. And there's no sign of any of that kind of stuff in the moon. So I think rather than giving up on the impact model itself, you have to think about, are there other ways of looking at that history? So that's a pretty good example of the kinds of things. Let's see, I'll go here and then.
Is there any recorded impact from space trash? I know we've left a lot in the atmosphere.
Yeah.
And I'm just wondering if anything's managed to slingshot its way into the moon.
Well, some of the objects that have been sent to the moon had deliberately crashed.
Right.
And I think
I know there's
more than one of the Apollo boosters, I think, crashed into,
Really?
was allowed to crash into the moon. It seems like if there was one, they would have, all 6 of them would have done that. But and then there's the Rangers I talked about, those early probes. They were fairly small, but they were deliberately crashing. So people have gone back to look for those craters, which gives you a little more clue about how much energy is needed to make a crater of a certain size.
Right.
So they are of interest.
But nothing accidental that we know of so far. It was just kind of like.
Well, let's see, there was just in a lot of the programs on television about Apollo 11. Remember the Russians launched one of their Zond probes virtually identical time. It was flying to the moon when the astronauts were flying to the moon in Apollo 11. And it was almost successful. It was setting down, but they didn't have as much information about the relief, and they probably didn't know exactly where the object was, but it stopped it hit a high mountain because everything was going fine, and it was about to start its landing procedure when suddenly it shut down. And so, yeah, that would have been an accidental one. Yeah.
You had a couple of your paintings on screen, as you didn't mention, you've been doing a lot of art in the last few decades. Talk about scientists doing art. What is
yeah, I'm not sure why I'm doing it. My grandfather was a painter and came from Switzerland in the 1890s or so we had a lot of his landscape paintings around the house. So I figured painting was okay, sort of subliminally. But I am kind of fascinated. I really got started by, who knows about the name of Chesley Bonestell? Anybody? Okay, so he was a painter who started with Life magazine in the 1940s. He did like a series of paintings in Life magazine of Saturn seen from each one of its moons. And he would figure out, if you're this far from Saturn, and we know how big Saturn is, then what angle does it cover in the sky? Our moon covers half a degree, but those inner satellites of Saturn, Saturn is filling up this much of the sky. So he would calculate that all out and make beautiful, realistic paintings. And it's amazing. That's one of the books I had when I was about 12. Willy Ley was one of the German scientists, and he wrote a book, and it was all illustrated by Bonestell paintings. And so that made me I used to sit down and try to make crayon drawings like his paintings when I was 12 or 14, and pretty much put it all away. Particularly in graduate school, because there was a real aura here that you know, real scientists don't do paintings, you know, you're not taking your graduate assistantship seriously if you're out doing paintings. So I didn't do much of it then. But I got back into it, not only because I like it, but I would go to meetings and people would announce a new discovery. And I thought, what would that actually look like, you know, if you were there? So I would, just for fun, I would make a painting of that. And then I'd take a 35mm slide and send it to the author of the paper. And I always had this feeling like, you know, this is teetering on a fence here. This could fall off in a bed. This could all go bad, or it could be okay. Because, you know, was I just going to get this reputation of this dilettante who was tinkering around, which I had a little bit of that reputation. But no, it kind of caught on, and it's because the idea was, well, you could use this, you know, when you're giving a talk to the public about this to show them what it looks like, and so that tended to catch on, and in fact, a group of us founded what we call the International Association for Astronomical Artists, and in 87, 88. We got invitations from the Russians, from the Russian Union of Artists, to come because they were riding high. It was the anniversary of Sputnik and so on. They had some Mars missions going. So we all got to go to Moscow and put on a big exhibit with them, which was fascinating. So that whole idea of astronomical art has been catching on more and more. And Tucson has annually a Space Fest, right, which is coming up. And a lot of it's centered around some of the astronauts, and you know, they line up at tables, and you could go pay money and get an autograph from one of the people who went to the moon, and so forth. But our group that I just mentioned, he always has an art show at that meeting. It's out at Star Pass. Yeah, thank you. Yeah, and coming up, do you know the dates off the top of your head?
August 8th to 11th.
8 to 11th on Star Pass. So that's something if you're interested in. So there'll be a lot of talks, but there'll be astronauts roaming around, and you can, as I say, go talk to them. And then we have paintings will be up, and those are starting to catch on. I like to just go out in the desert, or when I travel to like meetings in other places, take my paints and paint out of doors at places I've been. But part of that is that the way I say it is keep me honest about what rocks and trees and clouds actually look like, because you get in your studio and you end up just painting the rock the way, you know, this is Bill Hartmann rock here, Bill Hartmann cloud, and you see that in different artists. And so I try to get out in nature and work in nature. But we use that same idea in our astronomy group to go to exotic places that have similarities to planets. So I organized the first workshop in Hawaii, Volcanoes National Park on the Big Island, and you can go sit there and really see a lot. And most of them, just like me, I grew up in Pennsylvania. They grew up in places with leafy green trees. You know, never seen lava coming out of the ground, or lava rocks, or sand dunes, or glaciers, or things like that. So we've met in Iceland, and we've been to all sorts of different places. And you can kind of sit there and change the color to the sky color to an apricot color, and don't paint the bushes, and paint just the lava, and pretty soon you have a nice Mars painting. It's a plein air, it's an outdoor Mars painting, which is going to be hard on Mars. You have to have a big spacesuit on. Anything else? Yeah.
Given we're celebrating the 50th anniversary, I wonder if you could talk about what Apollo 11 and the Lunar landing meant to you on that day.
Yeah, I certainly had a lot of anticipation, because working as I was here, and in the darkroom in particular, it's kind of an interesting thing. That darkrooms were normally like 68 degrees, and so I would come out in the sun, and 102 felt pretty good. And so I'm walking over to the Student Union, and there's the moon, and I always used to think, oh, it's only going to go around like 20 more times. And then now it's only going to go around 10 more times. So there was this whole sense of being ready for it. But I have a kind of a funny story about the actual landing. My wife and I, we were just dating, getting together at that time, and she was working up at a museum in northern Arizona, and I went up to see her. And the staff of the museum all gathered at what's called the Colton House there, if any of you know, it's across the road from the museum. And they were all there, and moms and dads and kids, and we were all sitting around in the big living rooms, I remember. And they're coming around from the backside of the room, and they've got the audio on. I think it was Chet Huntley and David Brinkley, one of them said, "Oh, this is this momentous moment in the history of humanity. We're just going to let you listen to the audio between Houston and the astronauts, and they're starting their descent, and they're coming down." And this little boy would say, "Daddy, Daddy, Daddy, I have to go to the bathroom." And Daddy had to take him out to the bathroom during the landing. You know? And I thought, that probably made a good story 20 years later. But, you know, I don't think he was very happy at the time. So that was our landing story. So, thank you all.